In this video, I'm going to be going over every question we got in the study guide. What I recommend doing is first attempt each question on your own. I will be showing the answers to all of them at the end, so you can go to the end of the video, check your answers, and then the ones you need more help in, you can then flip through the video to where you need the help on those questions. So we're going to start with number 1. What does the law of conservation of energy state? So we've been talking about this for a while. We can't create or destroy energy. So energy can't be created or destroyed. It can only change forms from one form of energy to another form of energy. So looking at question number 2. It says how much heat is released when 250 grams of copper, how much heat is released when a 250 gram copper pot is cooled from 100 degrees Celsius to 20 degrees Celsius. So this is going to be a change in temperature equation, and we're finding heat. So our equation will be Q is equal to our specific heat times our mass times our change in temperature. And we could find each one of these. Our specific heat is going to be from copper. So we're going to have to check this table here. Specific heat to this column, go down to copper. And our specific heat is about 0.38 joules per gram Celsius. So we're going to put that in here. 0.38 joules per gram Celsius. Our mass, directly into question, 250 grams. And our change in temperature, this one I find tricks a lot of people. It's always going to be final minus initial. So it's always going to be what we end with. Here it's 20 minus 100, or it would be negative 80 degrees. Another cue here that it's negative is that we're releasing it. So if energy is released, our Q will be negative. So then what we have to do is just plug that in our calculator. So we can start with that 20 minus 100. Oops. 20 minus 100. And it's negative 80. And then we'll multiply by 250. And then times our specific heat, 0.38. And our answer is going to be negative 7,600 joules. All right, in our next question, we got how much heat is absorbed when 25 grams of iron melts at its melting point. So here we got a couple keywords. It's already at its melting point. There's not going to be a temperature change. So we know it's going to be Q equals mass times our change in enthalpy. Now our big question will be, is it enthalpy of fusion or enthalpy of vaporization? So it is melting. Melting is from a solid to a liquid. So that'll be our hint that we're using enthalpy of fusion. And then we can use our table. We're going through iron, enthalpy of fusion. So let's go down here. Iron, enthalpy of fusion, 209 joules per gram. And this energy is absorbed. And whenever we're melting, melting is endothermic, remember? So because we are melting, we're going to put our mass in. Because we are melting, our enthalpy of fusion will be a positive number. If we were freezing, it would be the same number here. Or not, sorry. That was 209, we said it was. If we were freezing, it would be the same number, but negative. But because we're melting, it's endothermic, it'll be a positive number. All right, so we got 25 grams. Let's get the calculator out here. 25 grams times an enthalpy of fusion of 209. Our answer will be about 5,225 joules. And it will be positive because that energy is absorbed. All right, so for our next question, we got a heat curve question here. How much heat is absorbed when 8 grams of ice at 0 degrees, so the melting point, is heated to water vapor at 100 degrees, the boiling point? So if we take a look, let's draw a miniature heat curve here on the side. And I'll zoom in for this one here. So a miniature heat curve. We got the heating of the solid. We got melting, heating of the liquid, boiling, and heating of the gas. And we have to figure out where we're starting here. So we are starting with ice. It's our solid at the melting point. So it'd be our solid right here. And we are ending with water vapor at the boiling point. So right here. So we have a 3-step problem. We have to figure out the energy to melt. We need to figure out the energy to raise its temperature. And we need to figure out the energy it takes to boil. So those 3 steps. And what those would be, the energy to first melt would be Q is equal to mass enthalpy of fusion the energy it takes to increase its temperature. Remember, it's starting at 0 and it's going to 100. So it would be Q equals specific heat of water times the mass times our change in temperature. So that change would be 100 minus 0, or 100 degrees. And then we got to figure out that energy to boil. And that would just be Q equals mass times our enthalpy. And boiling is from a liquid to a gas. So it would be enthalpy of vaporization. So let's stick all our numbers in here now. Mass is 8 grams. And our enthalpy of fusion, we're going to bust that same table out here. Enthalpy of fusion of water, 334 joules per gram. And because we are melting, it'll be positive. So 334 joules per gram. And we'll throw that all in the calculator right now. 8 times 334 equals 2,672 joules. Now let's figure out the energy it took to heat up and increase all that temperature. So we need the specific heat of water. So again, let's look at that table. Water specific heat, 4.184. Joules per gram Celsius times the mass, 8 grams. Mass has not changed. Times our change in temperature, 100 minus 0. Or we could have just written 100 there. Throw this all into calculator. 4.184 times 8 times 100 It's about, we'll round that to the nearest one number. So 3,347 joules. And lastly, we got to figure out how much energy it takes to then take that liquid water at 100 degrees and boil it so it's all a gas. So we can take that mass, 8 grams, multiply by our enthalpy of vaporization. So again, back to the table. Enthalpy of vaporization, 2,260 joules per gram. Throw this all in a calculator. 8 times 2,260. 18,080. Then what we got to do is add all those numbers up because that'll be our total energy. So we have 1880 right here. So plus 3,347 plus 2,672. And we got about 24,099. You know, we might as well just round that up to 24,100. Don't worry too much about rounding. I won't be grading off for rounding or anything. But if you add all these together, total energy, right about 24,100. Or 24,099. All right, so after this unit, we should be experts at labeling exothermic and endothermic. And I want to go back to kind of the definition. When something is exothermic, that means it's releasing heat. And that is the definition of exothermic. So exothermic right there. If something is endothermic, that means it is absorbing heat. So right here, endothermic. So those are just definitions. But we can use those definitions to help us with all the rest of these. So if our entropy is increasing, that means we're absorbing energy. So that one would be endo. And if we're losing entropy, our change of entropy is negative, we're losing heat, that'll be exothermic. For melting, I always like thinking of our heating curves. In melting, we need to absorb energy. We are warming up before and after melting. So we are absorbing that heat. Melting is endo, whereas freezing, we're cooling off. We are releasing that heat. Freezing is exo. For condensing, we would be going from a gas down to a liquid, releasing heat. That'll be exothermic. And boiling, or any type of evaporation, needs to absorb a lot of heat to go from a liquid to a gas. And that would be very endothermic. And then we also need to be able to tell these apart by looking at potential energy diagrams. So we got to think, on the left is the energy we start with in our reactants. On the right is the energy we end with in our products. So if our overall energy is going down, that means we're releasing energy. And that'll be exothermic. You can see our delta H here is going down. So that'll be negative. And in this one, you can see we have our reactants. We're starting with less energy than we end with. So we're gaining energy. You can see our delta H here. We're gaining that much energy. So that will be endothermic. All right, so now move into the second page. Question number 6. Question number 6, I have a nice diagram here. So we'll use this diagram. All right, and we'll start with, I guess we'll start with E and go across this way, because this is kind of a story. This is how it flows as far as time goes. So we'll go this way. So E is how much energy our reactants start with. So this will be the energy of our reactants. So let's look on our sheet. Energy of reactants would be E. There we go. And then in order for a reaction to start, we need to put a certain amount of energy in. And what I like to say is reactants, they start, with molecules and they're bonded together, or just compound in general bonded together. And in order to get our reaction to start, we have to break those things apart. We got to break them apart. And when we break those bonds apart, it takes energy to do that. That's why our energy goes up. So this A is referring to the breaking of our bonds. Let's see if that's here somewhere. Breaking chemical bonds. That would be A. And looking at B, this is an amount of energy. The amount of energy from what we start with to the tippy top right here of our transition state, that's our activation energy. So that's how much energy it takes to really get our reaction rolling. So B is our activation energy. And that's kind of where we have broken apart all our bonds, and you can notice we start releasing energy. So when we do the opposite of breaking bonds, when we start putting atoms together and forming chemical bonds, remember atoms? They like to have buddies most of the time, unless they're a noble gas. So they form more chemical bonds, and that releases a lot of energy. So this downward slope right here, D will be forming chemical bonds. And we're releasing energy. So you can see the energy we start with, and you could see the energy we end with. And C is that change right here. So this change will be our change in enthalpy. So from the energy of our reactants to the energy of our products, that is our change in enthalpy, also known as our enthalpy of reaction. So we could write C right there because that's what that represents. And then lastly, similarly, we started with the energy of our reactants. We end with our products. So this will be the energy of our products. So F is energy of products. All right, so the next question is all about entropy and whether it's increasing and decreasing. Remember our second law of thermodynamics. It states that entropy in the universe is always increasing. So a lot of the things that we see happen over time, unless they have some type of outside input in energy, that'll be what we think of as an increase in entropy. So when a balloon fills up with air, that won't happen by itself. Normally balloons empty with air. That's what they want to do. So when a balloon's filling with air that needs added energy, that would be a decrease in entropy, because that balloon now that's filled has a large amount of energy and the surrounding has a little bit of energy. So it's creating more of a energy imbalance. A hot drink cooling to the temperature of the room. That naturally happens over time. And that is a great example of spreading energy out, which is increasing the entropy. So this one will be an increase. An ice cube melting in a warm room. So that goes with the same thing. It is two substances that are in contact with each other becoming the same temperature. So that'll be an increase in entropy because that energy is spreading out. a gas becoming a solid. So we talked about solids are very ordered and they have very low entropy, whereas gases have a higher entropy. So when a gas becomes a solid, that is a decrease in entropy. Mixing sugar in a cup of tea. So whenever things mix, they're spreading the mass, they're spreading the energy, and that increases our entropy. Things naturally want to mix with each other. So increase. Your phone falling up into your pocket. So when it's falling up, it's actually gaining energy, which would not naturally happen unless you threw it up. So falling up, that's a decrease in entropy. That does not naturally happen. And then lastly, we've just learned this recently about Gibbs free energy. So let's take a look at these questions here. So it says, use Gibbs free energy to calculate the change in entropy when boiling water. Remember, so here's our equation, so we can write that down. Remember, right when a process starts to happen, that is when delta G goes from a positive to a negative. So use the reference table to find delta H, and the boiling point of water is 373 Kelvin. So we got some of our information right here. So let's write what we got down. We got delta G equals 0. We have temperature equals 373 Kelvin. And we have to use our table to find delta H. And this is of boiling water. So let's take a look at water here. Here's water. Our delta H of vaporization, 2,260. And that'll be joules per gram. So now we just plug all that in, and we're solving for delta S. So let's start. Let me change colors here as we plug our numbers in. We have 0 goes in for G equals our delta H is 2,260 joules per gram minus a temperature of 373 Kelvin times our delta S. So what we got to do is we need to add 373K delta S to both sides. So add it to this side, 373K delta S, and to this side, 373K delta S. And what we'll get after that, let me kind of draw